I'm going to now introduce categorization of data flow analysis, and the categorization is flow sensitive and flow insensitive analysis. In a flow sensitive analysis, the order of statements matters, and thus you need a control flow graph. And pretty much all the examples that we have discussed so far, most of them at least, were flow sensitive data flow analysis. The other category of data flow analysis is flow insensitive data flow analysis, where the order of statements does not matter, and thus you do not need a control flow graph. You only need a set of statements that occurs in the program. And so the analysis is the same regardless of the statement order. You can change the statement order and the results of the analysis are not going to change. So here are some examples of flow sensitive and flow insensitive analysis. So flow sensitive, constant propagation, liveness. So constant propagation, recall that depending on whether the last assignment was to a constant or not, it depends. That determines whether whether the variable is a constant or not. Now, if the last assignment, it depends on where we are in the program, and it depends on the order of statements and in general the control flow graph. Similarly, liveness depends on what is the first use going downstream, and whether there's a defined def of that variable, a defined an assignment to that variable before that use, and so on. So all these examples that we have discussed earlier, they are all flow sensitive examples. What is an example of a flow insensitive analysis? So let's say I was interested in all the variables that are ever used or mentioned or modified in a program. Now, in this case, irrespective of whether so let's say I'm mentioning X and I'm mentioning Y, irrespective of where they are being mentioned, the result is going to be the same. And so even if I reorder the statements, we're going to get the same analysis. Similarly, opcodes used in a program. So let us take this example of variables modified by a program. In this case, I'm going to define my transfer function and my meet operator. My transfer function is if there is an assignment of this form x colon equals e, then I basically say that this statement generates a variable, a modified variable, and in this case it's x. And the kill set is basically empty for every other instruction. So even for this instruction, nothing is getting killed because we are just interested in what are all the variables that ever appear on the LHS of any assignment statement. That means they get modified ever. And so the transfer function of any statement S is it takes the in, which is the value at the before the S, and then unions it with gen S, which is defined as such. And the meet operator is union. So for example, if there was an assignment to X and Y and Z, and this was the control flow graph, then the final solution will be X, Y, Z. Okay, and notice that the order doesn't matter. I could have changed X, Y, I could have moved X here, or I could have moved Z up. The answer would have still been the same. And that's why we call it a flow insensitive analysis. So, here is another example of a control flow graph where there's a three-way fork and each of them is basically assigning to the three different variables, and the answer is still going to be the same. In general, there is a flow sensitive analysis. Basically, you can identify a flow insensitive analysis if it is true that the solution you get for a sequence of statements S1 semicolon S2 is the same as what you would get for S2 semicolon S1, which is the same as if you take the solution for S1 individually and take the solution for S2 individually, and then you have some commutative associative operator that relates them. In this case, this is union. Okay, in this example, that was union. Okay, now flow insensitive analysis is nice because now I don't need to bother about the control flow graph at all. I can just treat all the instructions in the control flow graph and kind of completely break the structure of the control flow graph and treat those instructions as a bag of instructions. And then I can just run my fixed point algorithm in any order on this bag of instructions, and I'm going to get the same answer. So once again, what is the trade-off between flow insensitive and flow sensitive? Well, in a flow sensitive analysis, we require a DFA value at each program point. Because after all, the DFA value can be different at different program points, and we want to capture that. And that's what we have been doing in all our data flow analysis so far. So for example, we would track the DFA value at in and out of every statement S. Whereas for a flow insensitive analysis, because the control flow graph can be completely dismantled, we only require a single global value. maybe at the, in my bag of instructions, right at the beginning of that bag of instructions. And whenever I transfer across any instruction, any single instruction in the bag of instructions, I just update that single global value. So example, if I maintain the set of all variables modified, then if there's an assignment statement across which I transfer, I just say x colon equals e, then I say, okay, just take the variables modified by this instruction, which is x, and union it with this single global value. So I don't need to maintain a value at every program point for flow insensitive. I can convert, now here is the interesting fact, I can convert a flow sensitive analysis to a flow insensitive analysis by maintaining only a single global value and pretending that any of the program statements can execute non-deterministically and iteratively. So let us say this was my original program control flow graph, which has this nice structure. It's a diamond shaped structure, A, B, C, D. I just pretend that I completely break this structure and I just pretend that any of these statements can execute non-deterministically after any other statement. So maybe the first time C can execute, the next time it goes back in the loop, maybe B can execute, the next time it goes back in the loop, maybe D can execute. And so any of these instructions can be picked up non-deterministically and executed next. And so and I can use the same transfer function. So let's say I'm doing constant propagation. I can do constant propagation in a flow sensitive way on the original graph, when I maintain a value at every program point, or I can do the flow insensitive analysis for constant propagation, where I just pretend that all these instructions are completely independent and they can be executed non-deterministically one after another in any order. Now, the only issue is that if I do this non-deterministic execution of instructions, I can get less precise answers. So let's see this through an example, and I'm going to take the example of liveness. So let's say my original program was, the control flow graph was shown on as it is shown on the left. I am assigning to y colon equals y plus z, then I'm assigning to v colon equals w plus something, and then I'm assigning to x colon equals v plus something. Now, if I was interested in identifying the live values at entry, then clearly v is not a live value, because before the use of a v, there's a definition of a v. And so at this point, the value of v is not consequential to the program's execution, and thus it's not live. In fact, a simple usedef based liveness analysis, flow sensitive, will capture that. But if and so the flow sensitive solution is that at the entry, the live registers are w, y, and z. Whereas if I take the flow insensitive solution, I basically break this entire program into separate statements and pretend that any of them can execute non-deterministically. So now in this case, the third statement, which was x colon equals v plus something, can execute right in the beginning. And so v appears to be live at entry. So in the flow insensitive solution, it's a less precise solution because I'm also saying that v may be live at entry. So in general, so first of all, I can always convert any data flow analysis which was originally formulated as a flow sensitive analysis to a flow insensitive analysis. All I need to do is I basically need to pretend that my control flow graph is just a bunch of statements which can be executed non-deterministically one after another. And this can be done by pretending that your control flow graph basically has this fork at entry to all these statements, and any of these statements can execute non-deterministically. So there's a choice operator which basically saying which one gets chosen, and then and they all meet here and then they loop back. So it basically represents that any of these instructions can execute after any other of these instructions. And so once you change this control flow graph to this one, then you can just run your original maximum fixed point iteration algorithm for data flow analysis on the collapsed graph, and then you will get some solution. And let me call that the MFP flow insensitive, or MFP FI. That's a maximum fixed point flow insensitive solution. And the claim is that the precision of the maximum fixed point flow insensitive solution will always be less than equal to the precision of MFP of the flow sensitive solution. And here the less than equal to is based on the partial order operator of the semi-lattice. So recall that we also had in the previous module said that MFP-FS is less than equal to MOP-FS and so on, and ideal and so on. But so, MFP-FI is even less precise than MFP-FS, but it is going to be more efficient. Okay, let's also look at another example. So this is the example of constant propagation, and this example I am basically, I have this variable called step, which I initialize to 2 in the beginning. Then I initialize sum to 0, I to 0. And then this is like a for loop which increments I by step on every iteration and sum by I on every iteration. And then goes back to the loop. And if I becomes greater than n, where n is a parameter, then I exit the loop and return sum. Now, I'm assuming here that these variables step, sum and I are freshly allocated variables. That means they don't exist at the entry of the function. They've been allocated here and then used in the body of the loop and then deallocated at the very end of the program. Okay, so now if I run my constant propagation algorithm on this program in a flow sensitive manner, then I'm going to get some solution. And the solution, so if I run my constant propagation algorithm on this original CFG in a flow sensitive manner, then I'm going to say that at this point, for example, step will be equal to 2 and sum will be equal to 0 and I will be equal to 0. But at this point here, I and sum are no longer constants. And at this point, step is a constant, but I and sum are not constants and so on. But let's see what happens if I convert this program and this analysis into a flow insensitive analysis, in which case I'm going to break down this entire control flow graph into a bag of statements. And I do this by showing this kind of bag of statements where all these statements occur and any of these statements can execute non-deterministically. And then I pretend that there's a loop, there's a meet point and there's a loop, just like I'd shown you in the previous slide. And then I run my fixed point iteration algorithm on this collapsed program. Now if I run this fixed point algorithm, then notice that all the variables, like for example sum and I guess, they are being assigned twice, and so they are not constants. But step is only being assigned once, and it's being assigned to the value 2. And so the solution that I'll get with the flow insensitive analysis is that step equals 2, and that's a fixed point solution for the flow insensitive formulation of the problem where the whole control flow graph has been collapsed. Recall that the flow sensitive algorithm was much more precise. For example, the flow sensitive algorithm said that at this point, all three, step, sum and I are all constants. But in the flow insensitive solution, I'm just saying that step is a constant, but I'm saying that both sum and I are not constants anywhere. Okay, so, but let's say that I convert this program into SSA form. And we already know what SSA means. It's a single static assignment form where every variable is assigned exactly once. And you have 5 nodes to basically represent the fact that 2 versions of the same variable are flowing at that node. So for example, in this program, I get step 0 equals 2. So I get 0th version of step, sum 0 equals 0. That's 0th version of sum, I 0 equals 0, 0th version of I, and so on. Similarly, I create a 5 node because there's a loop edge. So there are 2 incoming edges to this loop head. One from the initial entry and one from the back edge. And I'm flowing in 2 values, 0 and 1 for I. And similarly, I'm flowing in 2 values for sum 0 and sum 1. And so I say I2 equals 5 of I0, I1, sum 2 equals 5 of sum 0, sum 1. And then I say, I check the condition. The current version is I2. So I say if I2 is greater than n, then go to end. I say I1 is equal to I2 plus step 0. So because this is a new assignment, I cannot, the versions I have for I are 0 and 2 so far. So I use a different version. In this case, I use 1. So the I1 equals I2 plus step 0. Similarly, sum 1 equals sum, I should say sum 1 equals sum 0, sum 2 plus I1. And then I say go to loop. Right? And then finally, when I exit the loop, I just return sum 2, because that's the 5 node that's flowing into that. That's last assignment to sum that's flowing into the return statement. I'm sorry for the errors. Okay. So there are these errors that need to be fixed here. So I'm just erasing the ones that have an error. So if I run this, then the solution to my DFA analysis for the flow insensitive case is step 0 is 2, because if I just consider this as a bag of statements, then step 0 has exactly one assignment, just like it was in before, and step 0 doesn't have any other assignment. Sum 0 also has only one assignment. The other assignments are to sum 1 and sum 2, which is a phi node, which I've kind of just encapsulated in this category called phi nodes. Similarly, I0 has only one assignment, I1 has exactly one assignment, and I2 also has one assignment, which is the phi node, and so on. And if I run the flow insensitive analysis on this graph, pretending that all these instructions, including the phi nodes, are independent instructions and can be executed non-deterministically one after another, then the solution I get is step 0 is 2, I0 is 0, sum 0 is 0, and you cannot say anything about the other variables. For example, sum 1, I1, sum 2, I2, etc. They are basically, we determine them to be not a constant. Now, the interesting thing I want to point out here is that the precision of the solution of this flow insensitive analysis after I did the SSA is identical to the precision of the solution that I had with the flow sensitive analysis. In the flow sensitive analysis, I wanted to say that at these points here, where sum 0 and I0 were active, then sum and I are also constants. And that is being captured by the fact that the versions, the respective versions I0 and sum 0 of the variables I and sum are 0, but then the other versions I1 and sum 1 are not a constant. And so that's an interesting observation, and we're going to carry that forward. But before that, I want to say that what is the transfer function of a phi node? So if there's a phi node, for example, I2 equals phi of I0, I1, then I just take the mean of whatever is the value of I0 in the in, and whatever is the value of I1 in the in, and let's meet them to assign it to value of I2. So just like I have a transfer function for every normal program statement, I also, once I'm doing it on SSA, I also need to say what is the transfer function on a phi node, and this is how I define the transfer function on a phi node. I just take the individual values on the RHS of that phi node and meet them using my meet operator to obtain the value for the LHS of the phi node. So the important observation here is that the precision of the flow insensitive plus SSA algorithm is identical to the precision of the flow sensitive analysis, which I've shown in purple here. So the purple values here are the precision of the flow sensitive analysis, where I'm copying the value at every program point. But on the right, in the blue, I'm showing the solution for a flow insensitive plus SSA solution. And the amount of information carried in both is exactly equal, because when I say step 0 is 2, then I basically mean that wherever it's the 0th version of step which is active, which is reaching, then that at that point step is 2. I0 is 0, same thing. Wherever it's the 0th version of I that is reaching, then I0 is 0, and similarly sum 0 is 0. Right, but I cannot say anything about all the other examples. So this is great, because if I would like to generalize this from the example. If the tracked program values are SSAized, which means the program is converted to SSA, then the maximum fixed point solution obtained by running the fixed point iteration algorithm on the SSA program with flow insensitive setting, which means I completely collapse the control flow graph, is the same as the precision of the solution that you're going to get without collapsing the control flow graph, which is represented by MFP flow sensitive. So precision of SSA plus flow insensitive is equal to the precision of flow sensitive. Whereas the speed and the space of flow insensitive plus SSA is significantly better than the speed and the space of flow sensitive, because in flow sensitive I have to copy the value at every program point, but in flow insensitive I can keep a single global value for the entire program. And so the speed of flow insensitive plus SSA is significantly higher than the speed of flow sensitive, and the space of flow insensitive plus SSA is significantly lower than the space of flow sensitive, space requirement of flow sensitive analysis. So this is a great improvement. So far we've been discussing our data flow analysis as a flow sensitive analysis, but for improving its running time and space complexity, I can first convert it into SSA and then use a flow insensitive analysis to get much better speed and much better space without losing any precision. And the typical implementation for this kind of an algorithm is that you use a single global value for the entire program. You convert the program into SSA, which means that the value size can increase slightly, because when you convert it into SSA, you create more variables, because each variable can have multiple versions. So you increase this value size by some degree, depending on the shape of the program. But now you don't have to copy the value at every program point. You can have a single global value. It's a larger value, but it's a single global value. And then you run the DFA fixed point procedure, just like the Kildall's algorithm that we have discussed, on the original CFG, just like before. Okay, so you don't actually dismantle the CFG, as I've been saying in the previous slides. You run the fixed point procedure on the original CFG in the reverse post order if it's a forward DFA, or in the post order if it's a backward DFA, or you can use regions as we have discussed in a region-based analysis. And on a transfer, you just transfer the value across a statement S by just saying out equals fs of in. And in this case, recall that this is just one global value. So I say in global to say that this is one global value. So whenever I create an out value, I just apply the transfer function on in global to obtain an out value. And then I meet the out value with the in global to update that global value. And on meet, I don't need to do anything. Okay, so on transfer, this is what I do on the original CFG. So whenever I go across a statement, I transfer across that statement and eagerly meet with the global value. So on every statement, irrespective of whether it's a meet point or not, after transferring across every statement, I meet with the global value. And which also means that when there's an actual meet in the control flow graph, for example, there was a meet in the control flow graph, then I don't really need to do anything, because actually I don't really care about the control flow graph structure in the flow insensitive analysis. And this is a typical implementation. And what is the advantage of this implementation over just completely collapsing the control flow graph? Well, if I run the DFA fixed point procedure on the original CFG in some kind of order, for example, reverse post order, then I am keeping track of what are the likely places which I need to transfer next. Just like reverse post order gives you better running time, because it just tells you what is my work list and what should I look at next. This method, even for flow insensitive, gives you better running time, because it allows you to keep track of what you should be looking at next. It allows you to order the inspection of different statements, even though from a precision point of view, the statements are completely unordered, but from an algorithmic inspection point of view, you order them in reverse post order or post order, depending on whether it's a forward or a backward analysis, and that gives you even better runtime than if you completely disregard the order and you try to randomly pick a statement from anywhere in the program. So that instead of picking a random statement every time, you only pick the things that are whose in values have changed because of fixed point algorithm, and the RPO or the PO helps in determining that. And that's why we call this a typical implementation.